Hello there, this is Space Advocate. A topic that is quite important for any future human exploration of Mars is the travel time required to get there. The issue of how long it takes to get to Mars radically impacts a wide range of challenges with missions to Mars, including radiation exposure, propellant boil-off, payload capacity, the amount of consumables needed like water and oxygen, and for crew, time spent in weightlessness, psychological impact, etc. I wanted to put out a video looking at this issue, perhaps clearing up some common misconceptions. This video will be divided into 4 parts with the timestamps below. Fundamentally, there are 2 types of missions to Mars. There are uncrewed missions and there are crewed missions. This dividing line affects a lot of the priorities going into mission planning, including how fast you plan on getting to Mars. For uncrewed missions, things are relatively easy. Machines can be perfectly designed for the conditions of the mission, and if the mission fails, that's unfortunate, but you can always build another payload and try again. Crewed missions are hard. You can't redesign humans for the conditions of the mission. Meeting human needs are an unyielding requirement for any crewed mission. That includes food, water, air, personal space, exercise, sleep, security, a sense of connection and purpose. There's almost no end to the list of human needs, and every need must be met for a successful mission. Most of the mentioned needs are affected negatively by being in space. Space is empty, devoid of resources, awash in radiation, and lacking even gravity. A force that is essential for our health and well-being. Preferably, you want to be on Earth. But even Mars is better than being in space, at least with current technology. On Mars, you have some gravity, perhaps enough to keep healthy over long durations, and you have resources, an atmosphere of mostly CO2, but also some nitrogen and argon, which can be made into breathable air. You also have some protection against radiation with the regolith and the atmosphere. With Mars being better than space for humans, any crewed mission to Mars should do what is possible to minimize the time spent in space, instead spending as much of the mission on the surface of Mars as possible. The duration of a conjunction type mission will generally be in the area of 30 months, plus minus a few months. It could be 9 months to get there, 15 months on the surface, and then 9 months to return to Earth. Or it could be 3 months to get there, 21 months on the surface, and then 3 months to return to Earth. The latter would be the better choice for the crew. It would cut down the amount of time spent in space by 2/3 or a full year, while also reducing the total mission duration by around 1/5 or around 6 months. I hope you have an understanding why getting to Mars quickly is important for the crew. Now, in the next part of the video, I want to look at some of the trajectory options available to the mission designers. To do this, I'll be using the NASA Ames Research Center Trajectory browser. This is a freely available website that is easy to use and has a database of trajectories for traveling to various objects in the solar system with delta V requirements and flyby speeds. If you're interested in that sort of thing, it's worth checking out. Using the trajectory browser, I've selected a few different options for trajectories going to Mars. They are by no means representative of every option, but they are some of the most relevant options that have been proposed for Mars missions. The first option I want to look at is the regular Hohmann transfer. This is generally the most efficient way of getting to Mars, which is why it has been selected for most historical missions going to Mars. In a Hohmann transfer to Mars, you perform a Mars injection burn in low Earth orbit that raises the highest point in your orbit around the Sun to precisely touch the orbit of Mars on the direct opposite side of the Sun. This has to be timed very exactly, so that Mars is at that point in the orbit at the time you arrive there. The biggest advantage of a Hohmann transfer is that it is efficient, which means you can use less propellant or carry more cargo for the same amount of propellant. Also, when you arrive at Mars, the velocity difference between the spacecraft and Mars is low, which means it's easy to enter orbit or land. While the biggest downside is the travel time, which is around 8.5 months. Moving on to the next option, a free return trajectory. There are many free return trajectories, but specifically I want to look at a free return trajectory with a low duration for the total trip, which is also a very similar orbit to an outbound Aldrin cycler orbit. What you get with this is an abort option, and in the Aldrin cycler application, a larger reusable habitat. In a free return trajectory, a single burn in low Earth orbit puts you on a trajectory to get to Mars and then subsequently return to Earth. To avoid going back to Earth, you have to actively slow down at Mars to get into an orbit or land. That means that if you uncover any serious issue with the spacecraft during the transit to Mars, you simply delete Mars from the itinerary, returning to Earth roughly 2 years after the mission started. And if everything goes well, the transit time to Mars is good, at 4 to 5 months. For an Aldrin cycler, the idea is to have a space habitat that repeats this orbit again and again, and you would use a small spacecraft to hop on at Earth and hop off at Mars. But a downside of the Aldrin cycler is that you need more than one habitat for all the advantages. The inbound Aldrin cycler is needed for a fast return to Earth. If you have a single outbound Aldrin cycler, a return to Earth using the cycler would take around 18 months, and the full mission duration would be in the area of 4 years. But if you have a second Aldrin cycler on this mirrored trajectory, the return could also be in the 4 to 5 months range, and the total mission duration would be around 2.5 years. To sum up, the primary advantage of this trajectory is an abort option all the way to Mars, but you also get there fast, and you could have a larger reusable habitat. But the biggest downside is that the velocity difference between the spacecraft and Mars is high, which means it's difficult to enter orbit or land. And this trajectory is less efficient than a Hohmann transfer. With an Aldrin cycler, that downside can be mitigated to an extent. And lastly, I wanted to look at a fast transit. This is the option to go for when getting to Mars quickly is the priority. It's where you use all available performance on your spacecraft to just go straight to Mars as fast as possible. This is one example of what a fast transit might look like. The more propellant you use, the shorter you can make the distance covered, and the faster you can cover that distance. Aside from the speed of light, there is no firm limit on how fast it's possible to get to Mars, but the faster you want to get there, the more expensive it gets, and you will also start running into issues where current technology doesn't cut it. You can go from chemical propulsion to nuclear fission propulsion to nuclear fusion propulsion to even more exotic theoretical propulsion systems, continually reducing the travel time. The major advantage here is of course that it is fast, but it comes at a cost in terms of propellant use and cargo capacity, and a major downside is that the faster you go to Mars, the more velocity you have to get rid of when you get to Mars. That means you either need a very capable heat shield and a robust spacecraft and cargo that is able to handle high g-forces, or you need to slow down propulsively, which adds to the cost in terms of propellant use and cargo capacity. Now, in this next part of the video, I want to look at what's possible with current technology, and more specifically, I want to look at the capabilities of the SpaceX Starship with the current plan design and architecture. I have chosen to look at Starship because it is the first crew-capable spacecraft expected to reach Mars, and it is also a spacecraft designed for getting there fast. There will be some guesswork here as to what the actual capabilities are or will be, but Starship doesn't use any fundamentally new technology, so even if I miss a little on what Starship actually ends up being, it still shows what's possible with current technology. To give some background on Starship, it is the current rocket development project of SpaceX, intended to replace the Falcon 9 and Falcon Heavy. It's a fully reusable, super heavy lift launch vehicle which SpaceX intends to use for satellite and crew launches. They have also been awarded a NASA contract for using it as a lunar lander, and the ultimate goal is to colonize Mars. The first orbital test flight is currently imminent, and will probably already have occurred by the time this video is published. For a Mars mission, the proposed architecture would launch a Starship on top of a super heavy booster. This is the largest rocket ever created by humanity, standing at 119 meters tall and massing over 5,000 metric tons when loaded with 150 metric tons of crew and cargo, as well as 3,600 metric tons of liquid oxygen and liquid methane. Once the booster has burned through almost all of its propellant, the booster would separate and return to the launch site, while the Starship would continue to low Earth orbit. In low Earth orbit, the Starship would rendezvous with an orbital propellant depot or Starship tanker. It would dock, and 1,200 metric tons of propellant would be transferred to the Starship. The Starship would then undock from the propellant depot or tanker and perform a Mars injection burn, setting it on a trajectory to Mars. Then it would enter the coast phase, lasting a number of months, where you might see some minor course corrections, but for the most part you're simply waiting to arrive at Mars. Eventually, the Starship arrives at Mars. Although it hasn't been officially stated, Starship could at this point perform some sort of entry burn. Of course, that is only possible if it has excess propellant to burn. Then comes the entry into the Martian atmosphere. But first, I'd like to point out this fact from the animation. This is the most recent official information of the highest velocity Mars entry Starship is capable of surviving, which is 7.5 kilometers per second. That's for direct hyperbolic entry, but SpaceX has indicated that they could perform multiple passes through the atmosphere, allowing for more time to bleed off velocity, meaning the Starship would experience lower peak heating and lower peak G-forces. Performing multiple passes would also allow for additional course adjustments, which could be needed for landing at a very exact spot on the surface, like a base or propellant depot. And entering a Mars orbit before making the final approach for landing could also allow Starship to drop off satellites in orbit. Regardless of the exact events here, Starship would at some point slow down to suborbital speeds, falling in a steeper and steeper trajectory towards the ground. The Martian atmosphere is so thin that as Starship approaches the ground, it is still traveling at a speed of around 500 meters per second. It will fire up a number of engines and perform a landing burn, bringing the velocity all the way down to zero, just as the altitude reaches zero. Before moving on to the next part, I want to list some of the assumptions I've made. These figures are based on rough calculations using known parameters and best guesses. As mentioned previously, the assumptions may not be entirely accurate, but they should be in the ballpark, and sufficiently accurate that the conclusion of the video wouldn't change with more accurate figures. Now, if you're not familiar with the concept of delta V, it is the velocity difference that the engines can impart on the spacecraft by burning propellant. It is basically a measure of how far your rocket can go before running out of propellant. With 150 metric tons of cargo, you have 6.07 kilometers per second of delta V, but if you reduce the payload to 30 metric tons, you bump that up to 7.84 kilometers per second. Additionally, less payload means that the Starship is lighter relative to its aerodynamic cross-section, and as a result, it has a lower terminal velocity on Mars. That allows you to get away with a smaller landing burn. That means that when you reduce the cargo from 150 metric tons to 30 metric tons, you get almost 50% more delta V to play with for the transit. Now, to look at the specifics of the Starship, I have compiled a list of trajectories from the trajectory browser and processed it, resulting in this table. The ones in green are within the delta V capabilities of Starship, while the ones in red are not. To shorten the list a bit, I'll remove the ones in red. That leaves us with this list, but getting there is only half the challenge. The next part is actually being able to land. Now, these are the flyby speeds at the Mars encounter. Green is within the official capabilities, yellow is what I estimate to be realistic with multiple passes, and red is not survivable. Immediately, you can see that down to 6.3 months is always survivable, so again, just to reduce the list a bit, I'll remove those. That leaves us with this list, which we'll look more closely at. If you look in detail at the dates, you can see that 2033 through 2035 are good years for going to Mars, while 2026 through 2029 are bad years. Most years you can push it down to around 5 months, and occasionally you can do it in as little as 3.7 months. But this is not the final answer. The Starship has excess propellant left over after performing the injection burn, even taking into account the propellant needed for the landing. So what if you use that propellant to do an entry burn? Well, if you use all the excess propellant to do an entry burn, that gives us this result. 3 trajectories that were previously red have now gone to yellow, and a couple have gone from yellow to green. But there is one last thing I want to look at. What if we reduce the payload? As mentioned previously, that gives us more delta V to play with. That brings us to this. 4 to 5 months is always possible, and some of the time you can get close to 3 months. And that is where I'm going to stop looking at options. As has been mentioned previously, it's always possible to improve the transit time. One way to do it would be to stage Starship in a higher orbit at Earth. A fully fueled Starship in geostationary orbit would have around 2 kilometers per second of extra delta V to use for the entry burn, but it would require a lot more tanker flights. Or you could use multiple Starships, like an expendable tanker Starship that would accompany the crewed Starship into a Mars transfer orbit, and then transfer additional propellant to be used for the entry burn. Or you could do both of those things, and more. But this analysis shows what a single Starship can do without deviating much from the official mission architecture. Lastly, I just wanted to show this slide from a SpaceX presentation from 2016. I didn't want to use this slide as a premise for the video, because a lot of the information is outdated, but if you look at the trip times for each year, they do roughly line up with the conclusions of my analysis, so it's an interesting cross-check. And that is it for this video. Please like and subscribe. And if you don't feel like doing that, then please at least give me some constructive criticism in the comments below. I'm always looking to improve. Thank you for watching and have a good day.